So it's interesting that we are going to do challenges and thrills. I think it's nice. Yeah, it's a long time I've seen that book. Yeah. Yes, of course. Yeah. And okay, so yeah, let me just write. It's a problem from challenges and thrills. Just writing the name of the book out of nostalgia, but okay. Yeah. So you can tell me the problem. Okay. So P is a polynomial with real coefficients. P of x is greater than equal to 0 for all real x. Okay. Okay. So show that Px is a sum of squares. Right. In okay. So sum of squares. Yes. Yes. So I did not write the other direction. That's why. So I believe it is to me it's easy because probably I've done it before somewhere, so that's why. So we know the following the that if alpha okay so every real root has even multiplicity. hmm is this my claim? Is it right? No, I mean not for any for px for our px. Because if it's an odd multiplicity, then we can just check. Okay, so proof. So suppose alpha is a so we will use this, right? Px is greater than equal to 0. So if it's a root with even multiplicity, and then you have qx which does not have a root, so then if px can be written like this and qx I should just write q of alpha is not equal to 0, right? Then you know that q of alpha, then without loss of generality, q of alpha is positive, right? Q of alpha is it's either positive or negative. I'm saying without loss of generality, we just assume it's positive. That's fine. So this implies by continuity that q of alpha minus epsilon and alpha plus epsilon is positive. This is uh, yeah, so this is a set actually, but yeah, it's understood what I mean. So this is positive. So really the sign only depends on this. Sign of P in a neighborhood depends on this, right? And then you see, yeah. So if it's an odd thing, then it will be negative. So this will be negative, and that's a contradiction. Yeah, and yeah, like yeah. I mean, yeah. So if let's just check it. So if Q of alpha is negative, then that implies that alpha plus epsilon minus alpha to k plus 1 is positive. I mean, that implies, or rather, this plus this implies that p is negative. P of this is negative, which is a contradiction. So every root has even, and geometrically you can see that this is what happens at an odd root, odd multiplicity root. Yeah. So all these things, this is fine. Yes, what remains will also be positive. So yes, and then just step by step you can do it. Right? How do you get sum of squares? Because the complex roots come in conjugates. So that you know, so a complex root will give you sum of squares. Or yeah, that is, let's see, I'm also sure. Px is positive. Uh, yeah, so let's just think about the complex roots. Yes, this is the sum of squares. This is the sum of squares. You can, because you can just complete it. And yeah, and just use the fact that modulus of real part of z is less than or equal to modulus of z. Like using that, you have to use that, right? So or something like that. So yeah, and then this is a sum of squares, and then you use the fact that product of sum of squares is a sum of square. Yeah, so basically we prove it for quadratics, and that's, and use the fact that for real roots have even multiplicity. So then this follows. Have yes, yeah. So yeah, so you take the even roots and you collect them, and that's a square, and the real roots, and the non-real complex roots uh, in pairs they form of sum of squares. Their multiplicity we cannot say, but yes. So this is fine. This is fine. Yes. 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 Okay. Oh, so that's another question you're going to say. Yeah. Sorry, yeah. Just a second, just me just address Srijani. Srijani, hi. We have just solved. Yes, we have just solved one question. So I suggest you can just note the question down and try to solve it later. Yes, since we have already solved it, but if you can, yes, yes, yes. Just pause. this problem also connects with one of so Hilbert had a collection of problems, right? So it yes, so one of Hilbert's problems connects with this. Um, right. So yeah, maybe we can think about it at the end, but it does connect. But what I can immediately suggest you to think about, and what I mean, not suggest or just what I am just thinking is, if I take a two variable version of this, if I take a two variable version of this, yeah, is the problem true for two variables? Simply R2 to yes. Because we used roots to solve the problem, but roots are not present in the question. So just okay. So yeah, I will think about it also. And so let me note it down. Then we'll move to the next question. Yes. Yeah, and the answer is no. The answer is no, and that is why. Yeah, there is a thing. The answer is no, and that is why the Hilbert's problem somehow comes, and it says that I mean it may not be a polynomial, but it's sort of, yeah. So it will be like a sum of squares of rational functions. So and in one variable case, that rational function maybe, yeah. So that rational function turns out to be a polynomial. So it's easy, but that version is much more interesting. Yes, I had once read that in yeah, in connection to model theory, but yeah, there is something called Tarski's transfer theorem, and that was an application of that. Basically, very interesting, I think, but we can talk about it later. Sum of squares. N variables, yeah, n variables. But we start thinking by two variables, maybe. Yeah, when we become professional mathematicians, then we can directly. I don't know, but yeah. Okay, let's move. Okay, so let's do one thing. Yeah, let's move to the next question, and after that, we will talk about some extension theorems. Okay. Yeah, Sujini had we had planned that we would discuss that also. But let's do the one more question. Try it. Yes. Yes. Okay. So F is from. Mhm. Ah, this is nice. See. Yes. 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 Right. So basically, yeah. So it's just enough to show for identity. Yeah. So why can't we just take some translations? So we take u equal to um, u equal to u of n equal to n plus 1 and v of n equal to n minus 1. Oh, yeah, of course. Yes, right. Yeah. That is- Yes, right. Okay. Injective, I got injective is fine. You just take 2n and minus n. n going to 2n and n going to minus n. Yeah, but this is going to start skipping numbers, and but there might be a way to come back. Why? Linear, right? Yeah, the right. Why? Hmm. Okay, right. Yes, yes, yes. Any linear will not work. I mean, yeah, other than translations or translation and in involution, like my n going to minus n and then a translation. Reflection translation, those are the only ones. Yeah, bijections usually we study the multiplicative structure. Structure, you want two bijections to add up to a bijection. Yeah. Yeah, you see, you basically just need to find two bijections that add up to a bijection. That's all. Then you can just invert that bijection. Yes, yes, yes. Then you can bring it back to identity by just inverting that. Yeah. So you just want two bijections that add up to a bijection. Yes. Yes. So just you can just think about is there some bijection which you can add to identity to get a bijection? It comes down to just that. Yes, yes. All those things you can do. Yeah. Hmm. Is this one surjective? Is this map surjective? Means if n is even, this is like if n is even, and this is if n is odd. If this is surjective, then we are done because it's injective. No, it is not surjective. Yeah, like 2, how do you get 2? This is never equal to 2. Like, 8 works, but like 2 doesn't work. Like as you said, so yeah, 6k plus 2 will not work. Well, 8 works. 8 works because yeah, because you take n equal to 3. Oh, what? No. Oh, 8 doesn't. Yeah. Uh, uh, yeah, 8 doesn't work, right? Yeah. It's not surjective. S- Yeah, yeah, right. 6k plus 2 will not work because. Okay, so wait. It has to be a constructive solution. Let's think about it. You want it to be, if you want it to be surjective, then 3n plus 1 by 2. We wanted 3n plus 1 by 2 there, right? Right. We are only getting 3n minus 1 by 2. We also want to get numbers of the form 3n plus 1 by 2. Right. So that's why I'm defining this kind of bijection and then add it to the identity. So uh, in the second case, but that would be that doesn't. The reason why I'm not putting, I was not putting this is, uh, oh yeah, there is what about n equal to 3 mod 6? Yeah, we don't want to leave it out arbitrarily. Yeah, mathematically that doesn't sound good. Yeah, that's the point. There is not much structure that we are able to use, so we have to think creatively, and that is what I'm lacking. Let's think about it for some more time, and then we should not give up like this. And then we can think in private later. Six. I'm just trying now from here. We are getting, after adding identity, we are getting, I'm just writing here in the corner, we are getting this function 3n by 2, uh, 3n plus 1 by 2, 3n minus 1 by 2. Is this function injective? Surely. Surely, because mod 3, right? Injective. And I am claiming that it is surjective because like 0 and 3 mod 6 numbers are taken care of by this. And uh, and 2 and 5 mod 6 numbers will be taken care of by this. Each of them actually takes care of two classes. And so every number mod 6 will be taken care of. But that's just a verbal thing. Okay. Uh, to prove it, you see, you just take like, just takes, let's say 6k plus 4. Okay. And my claim is that it gets taken care of by the last thing. And it is evidently clear. And now you can check every case. And so we are done. We had to just remedy the things one by one, fix the issues. Yes. Like you pointed out, right? It's 6k plus 2. There is a pattern. I mean, of course, there will be a pattern. One has to just realize what the pattern is. So that's why I went to 3 and then whatever that you see. We did it now. So yeah. 6k plus 3 is taken care by the first one. And it is, let's check if it is true. 6k plus 3 and it is, yeah, maybe it's 3 and my it becomes, yeah, it is, right? Good. Yeah. So it works. Yeah, it's good. I mean, yes, I mean, so we are dividing by 2. So that tells us that it takes care of two classes. That's uh, that is right. Yes. Yeah, somehow it's nice. Yeah. So as we pointed out that linear doesn't work, right? But just the next thing works, which is just the next thing to linear, right? The very next thing that you can think of without, yeah, so it's good. N is 5 mod 6. Yes. Oh, that's a good question. So, okay, so you're saying that this is not even a function. Ah, that's the problem, right? Okay. Well, yeah, that is a problem. Nice catch. So, yeah, n is 0 and 4 mod 6 is taken care of by this, right? When you say n is even, right? I am 1. Yeah, 6k plus 6k plus. Oh, right. Yeah, 6k plus 2 is also there. But 6k plus 3 is not there. Right. So it doesn't work. But now let us see as we wait. So what I so this is a partially defined function. Yeah, that was a problem which we ignored. from n uh, may not exist. You are saying may not exist. So what happens if I instead of looking at integers, I no, that is not. No, I think that can just complete this. No, because we are always dividing by 2. But let's see. Okay, so we have made a definition. Yeah, I think that this will be forced. We will be forced to complete this to a function in a certain way. That when you say 2 mod 6, right? So if this is equal to, yeah, if this is equal to 2 mod 6, then this is equal to 2. So I have this, right? And then I get 4. 4 minus 1 is 3. And this is, so n equal to 1. Okay. So so it's right. It's okay that it is 1 mod 6. Okay. But now let us see if we take, yeah, I think it's not going to work because wait. N is equal to 3 mod 6. Then, yeah, the problem is that 3 mod 6 fits in both the definitions, right? If it is 3 mod 6, uh, eh, yeah, and that is the ambiguity. Uh, uh, yeah, as you say, this may. Okay, let me just try one more thing. So if we want 5 equal to, yeah, so basically I think it should be, I mean, if it has to work, it should be something like 3 mod 6. So it is, uh, so what can it be modulo 12? Yes. If something is 3 modulo 6, then uh, modulo 12, what are the possibilities? 3 or 6? No. Did I say that right? 3 or 9, right? That's the correct thing. Yeah. 3 or 9 modulo 12. So I think that based on that, we have to say, uh, yes. So I'm thinking in that way. What is mathematically nice? I've sort of forgotten the problem, but that is not good. But it's, let us, yes, because 12 comes in the picture, right? While solving these equations, it was coming. So that's why I thought, let's see. So if it is 5, uh, wait a minute. Yeah, I think this should work. Okay, let's see. So if I take 5, and I want to solve it with this 3n, so I get n equal to 3, right? So so if this has to take care, you see from here we learn something, right? You see we learn something that that this I said that this takes care of 5 modulo 6, right? But actually it does not. For it to take care of 5 modulo 6, you also need numbers like 3, which are not 1 modulo 6. So yeah, so a 3 I will say 3 mod 12 then, because now we have to check if this is, because now it's a function, uh, and it is still is it still injective? Um, that should not be difficult. Yeah, this, let's check. So this will work. So if it works, then it's nice. Yeah, now it's a function, so that's okay. Is it injective? I mean, yeah, is this one even, what am I doing? Yeah, we have to check whether this one is a bijection. Did we check that earlier? No. Uh, I mean, we have to also check if this is a bijection, right? Yeah, is this a bijection? So let's call this F. So the question is F a bijection? And then we have to ask about the other one. Hmm. Hmm. Yes. Right. Yes. And of course, I mean, as you we can uniformly write it in terms of mod 12 also, but I'm not doing that. We can just, yeah. Is F a bijection? Let's check it. How? Hmm. Yeah. No, I think you're right. No, you're right. Yeah. So it is injective because this is injective without all this. Yeah, they are all distinct modular 12. And yeah, it's injective. Good. Now, why is it surjective? It should also be surjective because it's basically gotten out of a surjective thing, actually, some sense. But yeah, I think, yeah, because okay, so if you, what goes to 12? Yes, 24. So, yeah, is it a surjection? So if I take a k and if k is equal to 12k plus something even, so if k is It, it should not be difficult. Hmm. Okay. Yeah, why not? What about 12K? That thing should cover, right? Okay, okay, right. Oh no, wait. Let me not go with 12K. Just go with 6K. Yeah, I don't know. Yeah, 6K plus 1. Yeah, because if it is 6K plus 1, then 2 times that is 12K plus 2. And how do you get 12K plus 2? By taking 12K plus 1 and adding a 1 to that. Is it covered in the 1? Yeah, yeah, it is. Yes, if this is n plus 1, so yes, exactly right. And in that way, it is surjective. It will be. Yeah. So it's a bijection. There should be a better way to explain it, but somehow we are not able to. It's a bijection. And so it's a function. So now I'll just write on top of this, like if you take this function, this is also a bijection because we kind of checked it. Yes. I mean, this basically is following from the previous thing itself, right? Oh no, because n plus. Oh, because identity plus f. This is identity plus f. This is the thing, right? This is identity plus f. Now we need to check that this is a bijection. Yeah, let's check it. So, so I'm saying that this is almost something that we checked, but okay. So, right, what goes to 12? Yeah, this one, 3n by 2. 3n by 2 goes to 12. And so like if you take something like something which is 1 mod 6, let's say 6k plus 1, then you take this equal to 3n minus 1, and this is 12k plus 1, uh, no, plus 2, so plus 3. This is equal to 3n, and for this, n has to be uh, 4k plus 1. This is equal to n, and 4k plus 1, no, not anything mod 6. Yeah. Right. Uh, hmm, which one that is? Yeah, wait. So it's, I mean, no, I mean, we have to go with the last one because we have put our bet on that by putting here 3 at minus 1. Okay. So 4k plus 1 and 4k plus 1, then it is either 1 mod, right? But I think we need to look at it mod 12, right? And that is captured here, I think. 9 is there. Careful. Sorry. Yeah, wait. So n is equal to 4k plus 1. So n is 1 modulo 4. And uh, you're right. I mean, it's just 1 modulo 4. So any n which is 1 modulo 4 works right. So now just we need to say what can it be modulo 12. So n can be 1 modulo 12 and uh, if n is 1 modulo 4, then what can it be modulo 12? 3 can be 5 also and 9 also. That's all? Yes, that's all. So, right. So this is all. Oh, it cannot be 3? Yeah, it cannot be 3. Yeah. Okay. Let's see. It should be so. So if it is 12k plus 5, then it works. 12k plus 9 works. Right. So, but it can be 9 mod 12. Right. And that we have allowed here. Right. But wait. N has to be 4k plus 1. But I think we are making some mistakes, right? So if n is 4k plus 1, but it can be anything which is 4k plus 1. Uh, right? Yeah. And so modulo 12, it can be 1, 5, and 9. Uh, I, uh, yeah, modulo 12, it can be 1, 5, and 9. So we need to have all of them here. Uh, yes. Uh, ah, yeah, this is confusing, right? Yeah. So why don't you try to check it later, right? If you can do that, it will be great for me. Yeah. Vishujani, you should also check it if this is a bijection. And yeah, I hope it is, but yeah, because of it's just a check, so we have to. Oh, it's already 9, right? 9, 11. Okay. Yeah. Okay. So let's move on. And so, do you people have like 10 minutes? Maybe 10, 15 minutes. Maybe we can. I wanted to discuss its Titsegation theorem. So let's just do it. Um, yeah. So yeah. So basically, just extension theorems. Yeah, extension theorems. So yeah, let me just start this. Okay. Right. So again, I mean, the idea is let's start with the very basic case, which is question like this. So unit interval 0, comma 1. So if f is a continuous function, so this is really the question. This is the problem that we want to solve, let's say. So basically, I'm just going to mention the some elementary versions of these extension theorems which you should think about, and then we can discuss the generalization next time. Okay. So right. So let's say this is continuous. Okay. And the question is to find f, or rather maybe capital F from R to R such that f restricted to 0, comma 1 is equal to f. Okay. So want to find an extension. Let's try to do this now. Okay, I do not know how to do this. I mean, I can quote a theorem, but how can we do it ourselves, right? And then we can then I can some other version of it. So question is clear. So we have a continuous function on closed 0, comma 1. Extend it. Oh yes, yeah. So we just want to discuss extension theorem. So extension theorems are they occur in all kinds of generality. But here I'm just the first question is this: that given a function, given a continuous function on closed 0, comma 1, okay, can you find a function from R, from all of R, which extends small f, meaning that this capital F restricted to 0, comma 1 gives you the original f. No other restrictions other than this. I mean, yeah, continuity, continuous. Right, yeah, continuous, of course. Yeah. There will be many functions, yes. So what would a function be? Hmm, that's it, right? So this is the point. I mean that it's really very easy for close 0, comma 1. And for open 0, comma 1, if you ask the same question, you should say that you cannot do for some functions is not possible. So you should construct an example. Yeah, that it will not be possible. Okay. Yeah. So this is very simple. So it yes, that's certainly an obstruction, and it is, yeah, exactly. 1 over x is a counterexample. Okay. So this is a baby version of I mean of what is called the Tietze extension theorem. So, but I should ask some more interesting version of this, and then we can see. Yes. The problem is I do not know any other simple version. So one of the intuitions is that like if you are asking the same question in Rn, or like you can imagine R2, okay, then again the if the boundary is simple, right, then you can do the same kind of trick, right? If the boundary is simple, but if the boundary is not simple, then what do you do? Okay, that is the thing, right? Here the boundary is this like 0, comma 1 is the boundary, yeah. And if it's a circle, there's a boundary of the circle. You can do the same trick, right? So those are easy. But now the question, No, it's only about closed sets. I mean, this is about compact sets. You can compactness doesn't. Yeah, you can assume compact. Let's say compact closed. That's fine. But even then, it is a difficult. It can be a difficult question. For example, uh, for example, uh, no, that's connectedness, right? That's connectedness, right? Okay. So the question which I am thinking about is the following: you take the Cantor set, and there we ask the same question. Okay. So and this is what you can think about, and we can continue from here. Let's see, be the Cantor set, and f from C to R be continuous, because this is where now we cannot really play that game. Cannot just take the boundary and extend. Every point is a boundary point in the Cantor set. Yeah, but it's and I okay, in some sense maybe it is, but yeah. So extend f to all of R. Okay. Yeah, we can think about this. I will think about this. I mean, you can also think if you like, and we can continue from here. What we will be proving is for any closed subset of any topological space reasonable, some condition will come, normal and so on. But for any metric space, any closed subset, you can extend it. Okay. So yes, like we don't need compactness. So that's the a nice thing. And then we will continue from there. Okay. Yeah. Yeah, you can think about it. Okay. All right. All right. Then let's stop here today. Okay. So next time when we meet, maybe we'll begin with this. Okay. Because yeah, it should be better thing. And okay. Hmm. Okay. I would not know. Uh, okay. Uh, yeah, it's an open day. So okay. That's fine. So you cannot attend on Saturday. That's fine. It's okay. Yeah. Okay. Okay. That's fine. Huh. That's fine. Okay. Right. No problem. Yeah. Yeah. Okay. Whenever we meet next, I mean, these are the things to think about, and you can. Yeah. All right. Yeah. Okay. Thank